In the previous video, I discussed two different gates, the X and the H gate. Both of these gates are very important to quantum computers. However, there are more gates than just these. Two more common gates that are no less important than those two are the controlled X gate, or the CX gate, and the Z gate that I'm going to discuss in this video. As you can see, we're once again in the Blocksphere simulator that I used last time in the video. Similar to the X gate, the Z gate, which is what I'm going to discuss now, is named after what it does. In reference to a Blocksphere, it performs a rotation on the qubit around the Z axis of the sphere. However, right now, if I do a Z gate operation, you can see that nothing changes. But why this happens is pretty obvious, because the vector is currently pointing directly up, and so if you rotate it around the Z axis, which is on the facing directly up here, it's just going to rotate in place. However, if we first perform an H gate, and so put the qubit in a superposition, and so this vector is pointing horizontally, we can then perform a Z gate operation and have a more practical effect on the state of the qubit. And now this H gate, instead of returning back to its original position, is going to flip to be in the one state. The CX gate is a little different from the other gates, so I'm going to do it in the IBM Quantum Composer as opposed to the Blocksphere. We already know what the X gate does. It simply performs a 180-degree rotation around the X-axis, flipping the output of the qubit essentially. However, what a CX gate does is pretty different from other gates. There needs to be two qubits for it to be able to take effect. There needs to be a control qubit and an output qubit. So I'll demonstrate that here. So let's say qubit 0 is our control qubit. I'm going to place down a CX gate, which is this one, and for anyone who's interested, you can see the code using Qiskit on the right side here. Right now I have read-only access to this, and I'm trying to troubleshoot why that is. But as you can see, in the code at least, you create a quantum circuit, and we're performing a CX gate operation on the first and second qubit. And you can see in this histogram here that the only possible outputs are 0 and 0 for both qubits. And this is because the controlled X gate takes into account what the first qubit is and changes the output of the second one based on that. To be more specific, if the control qubit, in this case Q0, is equivalent to 1, then the CX gate will perform an X gate operation on the output qubit. And so in this specific scenario, Q0 is being read as 0, and therefore it is not performing the X operation on qubit 1. However, if we change that, if we perform first an X gate operation on Q0, we can see that in our results, we have 1 for both qubit readings. And this is because now it's this controlled X gate, it can see that this qubit is being read and measured as 1, and it then flips this qubit to be 1 as well. Now we can use the CX gate to do some pretty cool stuff, and by that I specifically mean entanglement. Entanglement is a concept that I've discussed previously in other videos, and the CX gate allows us to create entanglement. So right here I have built a circuit with this H gate right in front of the CX gate that will entangle the states of these two qubits. So as you can see in this bottom output here, they're always going to be measured as 0 and 0 or 1 and 1, so their states are entangled, they're connected. We can also create an opposite entanglement by simply putting a X gate at the end, so that we always have the states of 0 and 1 or 1 and 0. So we're basically making it so neither of the qubits can be in the same measured state. Entanglement allows us to coordinate the measured values of qubits that are in superpositions with other qubits that we want to match them with, or, well, unmatch them with. Entanglement is ultimately what allows quantum computers to be so much faster at certain tasks than traditional computers, and even understanding it on this very basic level is critical to later understanding. This concludes this video on more states and entanglement. I hope you're able to learn something. Let me know in the comments if you have any thoughts, questions, or ideas. And I hope to see you in the next video. Thanks for watching.